Just let me know when you're ready.
Yes, we can start now. So
Okay, perfect.
our next speaker is Matteo Braglia from New York, and he's going to talk about back to the features, and we'll see what these are.
Yes. So just for your information, can you see the pointer on my screen?
Yes, it's small.
Okay.
We can.
It's very small. You're right. Yeah. All right. Thanks, Anis, for the introduction, and thank you for inviting me to give this talk. This very nice seminar series. So today I'll try and get you back to the future. So what is the meaning the meaning of this title? So this talk is going to be about primordial features, and I will define in a second what these features are. So essentially, they are signals from the early universe that show up anytime you have violations of slow roll during inflation. And the reason of this title, the word back in this title carries the following meaning. So these features were, this topic was kind of popular earlier on, like a decade ago, before the first the first data were released by Planck, and then after the first data release, because there wasn't any evidence for this feature. It doesn't mean that they are not there, but Planck couldn't find any evidence. Um, this topic kind of got less popular over the years, and they have seen, and this topic has seen a resurgence in recent years in the context of a different kind of phenomenology, that is primordial black holes and stochastic gravitational wave backgrounds, where the models that give rise to this kind of signals can also be relevant, but it's in a different context, in a different regime of the theory. So today I will just stick to large-scale observation, large-scale cosmological observations, and I will present some hints of this type of signals that we can find in cosmic microwave background, and I will also discuss how we can test these signals with forthcoming experiments. Okay, so the outline of the talk is the following. I will first define what these primordial features are in a more detailed way. I will then move on to discuss the hints that we have in the CMB data, and in particular, I will just consider Planck data, which to date are the most constraining CMB data set. And given these hints, I will discuss how to test them with future CMB experiments, which will map the E-modes of the CMB with a much better accuracy than Planck at all scales. And this will significantly enhance, essentially, the significance of these primordial features if they are really there in our data. But let me start with a very, very brief and basic and pedagogical introduction to inflation. And I will just review the elements that I need in order to define what the primordial features are. And so I'll just go very, very quick. But if you have any questions, just feel free to stop me at any point. There's absolutely no problem. So inflation, as you know, was essentially engineered, was invented in the late 70s to solve the hot Big Bang scenario shortcomings. Essentially, this is a conformal diagram that is showing the causal structure of the space-time for our hot Big Bang scenario. And there is essentially an origin of time, which is at tau equal to 0 at this point. And we can immediately see the following problem. So if you look at 2 points that are separated, I think in this diagram they are separated by 90 degrees, but essentially that are far away from each other in the sky, 2 opposite directions. And we look at the CMB. We know that CMB, we observe a CMB which is remarkably uniform, remarkably homogeneous and isotropic. But these 2 points that are far distant could have never communicated in the past in the context of the hot Big Bang scenario. And so inflation postulated essentially an initial stage of accelerated expansion of the universe, which pushes the initial singularity at minus infinity in conformal time. And this provides a mechanism to wash away any initial inhomogeneity so that you're left with a highly homogeneous and isotropic universe. And also it provides a way to for these 2 points to have communicated in the past. So these 2 points with the initial phase of inflation can have communicated in the past. All right, so this is essentially the reason cosmic inflation was invented. And the standard scenario of cosmic inflation is low roll inflation. This is the simplest and the paradigmatic model of inflation. Okay, eventually, so we have a scalar field that slowly rolls down an almost flat potential. Eventually, it falls down the minimum, and we have a stage of reheating, but this is not going to be of our concern. So let's focus on this small patch of the potential for the time being. Okay. So the action of this scalar field, in the case of single field, minimally coupled and with slow roll inflation, okay, the action for the scalar field takes this form here. And we need to have, so we want a homogeneous and isotropic universe. So we require the metric to take this form, and the only consistent configuration of the scalar field with this metric is a scalar field which evolves only with time. There's no special dependence. These are the field equations. So in particular, the first one is the first Friedman equation, and then we have the Klein-Gordon equation that controls the evolution of the scalar field. And the condition for the universe to accelerate is essentially that this parameter epsilon b is smaller than 1. And then we have also, in order to have a consistent stage of inflation that solves the hot Big Bang scenario shortcomings, we need inflation to last long enough. And so we have a whole tower of slow roll parameters that need to be smaller than 1, and we usually refer to these conditions as slow roll conditions. Under these conditions, we can easily solve the Klein-Gordon equation, because if these parameters are small, we can essentially forget about the acceleration of the scalar field, and we have very simple analytical solutions for the evolution of the scalar field. So this is essentially slow roll inflation. Now, this is the background dynamics. What happens is that this is really quantum field theory, right? So on top of this background dynamics, we have also some very small, tiny spatial fluctuations for the scalar field. And these are essentially quantum fluctuations. So we can linearize the scalar field profile. The thing is a little bit more complicated because this is not flat space-time. We are in an expanding universe, okay? We need to consider GRs, and we also have metric perturbations, and in particular, but everything can be dealt with a very simple QFT in curved space-time. And as I was saying, we have also some metric perturbations, scalar perturbations represented in this case by this quantity, which is called curvature perturbation zeta. And then we have also tensor fluctuations. This gamma is essentially nothing but gravitational waves, although I'm not going to consider them in the following part of the talk. So essentially, this zeta is actually the most important quantity in cosmology, in early universe cosmology, because it's a quantity which is conserved on superrising scales. So it allows us to make predictions because it is not it does not evolve during the reheating era, which is something which is still a bit uncertain. Okay, and it is related to the fluctuations of the scalar field through this simple equation. So what we do is, again, this is quantum field theory, so we quantize this variable zeta. Okay, we have some creation and annihilation operators, and we have these mode functions zeta k. So these are essentially the Fourier modes of zeta k, because we are in linear theory. So these Fourier modes are decoupled. They follow some equations of motion. We can solve them, and the quantity that we are interested in, the main quantity we are interested in, is the primordial power spectrum. Is the power spectrum of these Fourier modes at the end of inflation. Okay, and this is important for the reason that I will see in a second. But for now, let me just tell you what is the shape of this primordial power spectrum during slow roll inflation. Now, it's a very simple textbook calculation, okay? And essentially, the shape of this primordial power spectrum takes the power law form, where the power law amplitude is given in terms of the Hubble rate and the epsilon, the first slow roll parameter, and the power law spectral index is given in terms of these 2 slow roll parameters, epsilon and eta. So by construction, these eta and epsilon are small by definition of slow roll inflation, and therefore a generic prediction of slow roll inflation is a near scale invariant spectrum of scalar fluctuations. All right, which in this language, because of an historical accident, corresponds to ns, which is more than 1. But because these are very small but non-zero, okay, so a prediction of zero inflation is that ns is not equal to 1. Okay, in particular, because there is a minus, in general, most models of inflation predict ns smaller than 1. Now, the important thing to realize is that the nice feature about inflation is that the primordial power spectrum of quantum fluctuations produced during inflation at the onset of these quantum fluctuations are stretched on super horizon scales. Eventually, they classicalize, and when they re-enter the horizon, okay, they are connected through essentially GR to density perturbations. So they source perturbations in the components of the universe. And what is important for the following part of the talk, where I will be considering the CMB, is the coupling of metric perturbations to photons. Okay, so essentially, from this primordial power spectrum, we can, again, this is really textbook stuff. We can compute, okay, the shape of the resulting. We can actually compute. We can predict the angular power spectrum of the CMB anisotropies. Here on this plot, I'm showing the map of the CMB temperature anisotropies. We also have map of the polarization, in particular the E-mode polarization of the CMB. Okay, and again, a given model of the universe cannot predict this map, but it can predict its angular power spectrum. So what we observe, what we do is essentially we observe the cosmic microwave background in the sky, we produce a map, and then we compress all the information on the map into its angular, we perform an angular spherical transform of this, and then we compute the primordial power spectrum, and this is something that we can compare to the theoretical prediction for the angular power spectrum, which is given essentially by, in a pictorial way, it is given by this quantity. So given a primordial power spectrum, which takes the formula I just shown, okay, we can convolve this primordial power spectrum with this transfer function. This transfer function does not depend on primordial physics. Okay, it is uniquely fixed by the evolution through radiation and matter-dominated era. Okay, so it is completely decoupled from the primordial physics. Okay, so and integrating over k this p of k, essentially we can compute the Cs of L. Now let's look into this transfer function closely. So here I'm plotting the transfer function for some multiples L as a function of k for temperature modes in the top panel and E modes in the bottom panel. Okay, so as you can see, this is essentially an integral over squares of Bessel functions. So it is a highly oscillatory function. But the main point is that it is very much picked around the given scale. Okay, this scale is essentially given by 1 over L. Okay, k is equal to 1 over L. So this means that we are projecting primordial perturbations on wave number scale over multiples. Okay, onto multiples. Which are given by 1 over L and a proportionality constant. Okay. Now we can in a very just to understand the effect of changing the parameters on the primordial power spectrum. Okay, you could think in a very naive way. You could think of these transfer functions as described by the main peak. Okay. So this main peak can be approximated in a very rough way, but this is just for the purpose of qualitative understanding. It can be approximated by step function. Okay, so you see that the power spectrum is essentially very smooth over this transfer function, so it can be pulled out the integral. Okay, and the effect is essentially to multiply this integral over the transfer function. So we see that changing the overall amplitude essentially moves this angular power spectrum up and down, and changing the overall spectral index simply tilts a little bit the angular power spectrum. Now, we have very explicit, very accurate measurements from Planck of this primordial power spectrum, and so we can use this to set constraints on these two parameters of our primordial inflation models. And it turns out that lower inflation is very well consistent with the data. Okay, you can see from this measurement of the spectral index of primordial scalar perturbations from Planck data that the exactly scale invariant power spectrum, which corresponds to ns equal to 1, is ruled out at several sigmas. Okay, and so we can already use this to start setting constraints on primordial inflation models. And these are some popular models. So in this plot, you can see on the y-axis the tensor to scalar ratio. As I said before, we also have tensor fluctuations. And we haven't detected tensor fluctuations, so primordial gravitational waves at large scales. Okay, so you see that for this reason, we cannot say that we have evidence for inflation. At the very same time, though, inflation, at least slow roll inflation, is very well consistent with the data. Okay? But because we do not have evidence, it would be very nice to have some handles, some additional signatures that we can use to constrain inflation, okay, with cosmological data. And this is precisely what I'm going to discuss in a second. And primordial features are essentially one such signal that we can use to learn something a little bit beyond slow roll, beyond the vanilla slow roll model. And essentially, these primordial features are some oscillatory signals that are produced by the kind of physics that we'll explain in a second. But for the moment, because I am already talking about the observational effects, let me just parameterize these primordial features as a small correction to these primordial power spectrums. For the moment, you can think of these signals as just a very small correction to the primordial power spectrum. And in particular, they are oscillatory corrections. Okay. Now, the observational effect of these primordial corrections can be understood as follows. If we have some oscillations in this P of k, okay, again, looking at these transfer functions, we can see that if the wavelength of these oscillations is larger than the typical width of these transfer functions at a given L, then that means that the primordial feature, okay, this signal is going to be testable, it's going to contribute to the overall Cs of L at that multiple. If, on the other hand, we have very high frequency oscillations, okay, compared to the overall width of the transfer function, these are going to essentially be washed out in the integration of Rk. Okay, so it is in order to see whether we can test these features or not. Okay, you have to compare them with the transfer functions at every single L. So this is going to be a scale-dependent signal in the Cs of L. Okay, and since I'm showing already this plot, let me also mention that one feature that is very nice about E modes, okay, is that the transfer functions are generically more peaked than the transfer function of temperature modes. So if you look at this plot, this is just saying that you can test higher frequency features compared to temperature modes. Okay, so we can parameterize these features again with some oscillatory functions in K. And you can see that depending on whether this oscillatory function oscillates with log K or K, because of the specific structure of the transfer functions, the signal will show up in a different way depending on the multiple that you are looking at. Okay, but one thing that is common to both features, okay, is, as I said before, that if you compare the signal in temperature, which is shown in the central panels, to the signal in the E modes, the signal in the E modes are going to be amplified relative to the temperature because of the sharpness of the transfer functions. Okay, so this is just telling us that E modes are a much better detector of T modes for these types of signal. Okay, so this was just a phenomenological discussion. Okay, so I just showed the effect of oscillation in the primordial power spectrum. Now, the question is there any hint to these signals in the data, or is there any way to consider the signals from the theoretical perspective? Now, let me start addressing the first question. Now, if we look, here I'm showing the measurements by Planck of the temperature of angular power spectrum. So if you look at the residuals, okay, you do see some kind of deviation from scale invariance. Okay, this could be interpreted as deviation from new scale invariance at very large scales, so very small multiples. And in particular, small multiples, you see a generic suppression of power together with the dip here, which is nearly 2 sigma away from zero. So this is what is usually referred to as Lowell anomaly. It was observed already by WMAP, but Planck data also brought up some very interesting oscillatory residuals at higher multiples, so smaller scales that were not mapped correctly, that were not mapped accurately by WMAP. Okay, so in principle, there is room for these features in the data. These are just anomalies. These are not evidence for new. These are not like significant detections on something which is beyond the CDM, but there is room for these features to improve the fit of the data. And then, from the theoretical perspective, okay, so the model of slow roll inflation that I showed before is essentially just a toy model, right? So we have a single scalar field, but anytime you try to embed these models in some UV complete theory, then you end up with multiple scalar fields, right? And so in a multi-field landscape, this looks like a really fine-tuned trajectory. So it's essentially a trajectory that looks like this. So you have very steep walls, and at the bottom of this multi-field potential, you have a straight trajectory which goes over a very smooth and nearly flat path of valley. So in this sense, this is kind of fine-tuned, but this is what you should really expect from a realistic multi-field landscape. Okay, so you should expect something which is a little bit more hilly. So you should expect turns in the trajectory, bumps, and steps in the trajectory, or whatever. And this, which looks like a more realistic, a little bit more realistic scenario, okay, is a scenario that could still provide inflation, meaning that you still have an accelerated universe, but temporarily you could violate and even significantly violate the slow roll conditions, okay? And this is going to translate into oscillatory corrections to the primordial power spectrum. So there is indeed a theoretical reason to consider these oscillatory corrections. And in particular, depending on the type of feature that you have in your background, you'll end up with different features in the primordial power spectrum. For example, you could have a sharp feature, okay? This happens anytime you have a sharp feature in the background, so a transient departure of a background quantity, be that the velocity of the inflaton or some derivative of the potential or whatever in a background quantity, okay, from the trajectory solution. So this is something that happens over a very short time, like an EFO or less than that. And for example, here I'm showing the celebrated Starobinsky model, 1992, where he proposed to have essentially a sudden change in the slope of the potential, and this is going to produce this type of signal. Now, the generic signature of this type of signals is a sign which is linear in k. And in particular, the interesting thing is that the frequency of this sign, this k naught, is nothing but the comoving wave number which crosses the Hubble radius at the time of the feature. Okay, and then the amplitude, the overall envelope of this oscillatory correction is extremely model dependent. But a universal signature is this running of the sinusoidal correction. Then we can have some more some other types of signals. So things like a periodic oscillation of a background quantity around the attractor. So in this case, we have a transient departure. Here we have a small periodic oscillation. So we have a background oscillation with a frequency omega, and the type of signal that will show up in the primordial power spectrum is a sinusoidal correction that runs with log k instead of k. Okay, and you can see that it is completely different. And then a third possibility, and this exhausts the zoology of feature, is a combination of them. And this is usually referred as a primordial standard clock feature. Okay, and this is, for example, given by a feature that occurs where you excite when there is an excitation of a classical oscillation of a massive field. So what excites the classical oscillation of the massive field is a sharp feature, and then the oscillations of the massive field provide a small periodic background oscillation that produces a damped resonant feature, which goes as log k in the primordial power spectrum. So this is more or less what we could expect from the theoretical point of view. Okay, and now the question is how to look for these primordial features in the data. And there are mainly two approaches. The first one, which is not what I will consider in the following part of the talk, is a model-independent approach. So essentially, you are agnostic to the model that is producing the feature. And what people do is usually they spline the primordial power spectrum and they let the data, reconstruct the primordial power spectrum. Now, an advantage of this approach is, of course, the model independence. So essentially, one is agnostic to the data. But on the other hand, the results are not necessarily physical, meaning that your parameterization is completely being agnostic. It doesn't necessarily have to reproduce something that you can reproduce with a physical model. Also, it depends. It is truly model independent, but there is a hidden model dependence, which is usually again hidden in the bidding that one chooses to perform the reconstruction. And features that are finer than the bidding cannot be reconstructed. And finally, this typically requires a large number of parameters. Now, the approach that will be taken is instead a model-dependent approach. So I will just start from a model, and I will derive the primordial power spectrum. Now, the disadvantage of this model is, of course, that you have to repeat the analysis, of these models for each of the models that you want to consider. On the other hand, if you don't have a problem with that, if you're okay with that, then there are a lot of pros for this approach. One advantage is that, of course, again, you have a much higher predictivity. So given a bunch of parameters, which is usually 3 parameters, in the models that we'll be considering, then you can just predict the primordial power spectrum, And in this way, also interpreting what you extract from the data is much simpler because you have a handle of what these parameters, predict on the theory. So this is the approach that I'll be taking in the following part of the talk, And now I'm going to show you an example of how this model-dependent analysis is performed. So I will start by building a model of primordial features, and then I will compare this model to the data and show you what are the information that we can extract from the data, and what are the hints for these models that we can see in Planck data. And I'll do so using a model of the primordial standard clock, which is the third possibility that I showed before. So this is a model where we essentially it's a multi-field model. So we have the inflaton, and we excite at some point the classical oscillation, background oscillations of a scalar field. So schematically, the type of signals that we are going to encounter will take the following form. We will have at large scales a sharp feature that has this signature linear oscillation, and this will be continuously merged to a resonant feature signal at smaller scales. So essentially, the first one will depend on the mechanism which excites the oscillations of the scalar field. The second one instead will depend only on the oscillations of the scalar field itself. And the physics, the kind of information that we can extract by detecting these two, the parameters of these models, again, this is just schematical, would be the following. So by detecting the sharp feature signal, we can tell something about the time at which the scalar field oscillations were excited during inflation. And by detecting the frequency of the resonance signal, we will be able to detect the effective mass of a scalar field, which is excited during inflation. So this is the type of beyond slow inflation information that we can extract by measuring these parameters. Now, this is really schematic, and it's just a naive explanation of what we are going to see. But let me consider a specific model. So this could be an example of a primordial standard clock model. So this is essentially a multi-field trajectory, and different colors represent different values of the multi-field potentials, where redder colors correspond to lower values of the potential. So essentially, this is the bottom of the potential, and then we have walls that go up at the borders. So the trajectory that we have in mind is the following. So first, we have a brief slow roll, a local in time slow roll trajectory. And then at some point, the trajectory enters a curved path of valley. Because of the initial velocity, the trajectory overshoots the minimum, and this is the sharp feature, okay? And this sharp feature is going to excite the classical oscillations of a massive field, which are represented by this trajectory oscillating around the true minimum, okay, which is the yellow one of the potential. And you can see these oscillations dying down at higher as the trajectory goes along the minimum. So this is an example of the trajectory that we have in mind, and it can be simply implemented with this Lagrangian. So we have the theta is the inflaton. The inflaton potential is modeled as a simple Hilbert potential here. It could be modeled by any other type of potential. And then we have a massive scalar field. Now, the way that we introduce the bending trajectory is through this kinetic coupling to the kinetic term of the inflaton. And you see that as the trajectory enters the curved path of valley, this sigma, this massive field, which was lying at the bottom of its potential, gets excited to a new effective minimum. Okay, but as it gets excited, it undergoes some damped oscillations around it, and this is the type of feature. This is essentially the scale dependence of the primordial power spectrum that we are going to observe. So you see at large scales we have a sharp feature, and this is continuously merged to a resonant feature at smaller scales. So we took this model. Okay, this was just a toy model, of course, but it represents a very the physics is quite clear. Okay, so there are some signatures of the massive fields, and signatures of the sharp feature, etc., and so on and so forth. And so our goal was, after building this model, how to compare it with Planck data. Now, things are not extremely simple, and the main reason, and there are many, many reasons to why the things are not simple. First of all, comparing these models to data is a computational mess, and the reason is that there is no analytic way to solve this, to solve the mode functions, okay, and to compute the power spectrum of primordial fluctuations. So we have to solve essentially the full background and perturbed equation of the sigma and the theta field. And this is a computational challenge, okay? So we had to implement a numerical pipeline to do so. And we were the first ones to actually compare these multi-field feature models to the data. So this was although this is nothing that is conceptual, it was a numerical, essentially a numerical challenge. And then there are also some other challenges that are associated to the interpretation of this data, because when we have these oscillatory signals, okay, we know that we have some that we have to expect multi-model distributions and so on and so forth. And also interpreting the posterior distributions of the model parameters is not clear. If you just input the parameters the Lagrangian, the parameters in the Lagrangian, then they are very degenerate. So the interpretation of the analysis is not clear. So what we had to do was, starting from the model Lagrangian, first of all, we had to derive some effective parameters that describe some distinct property of the signal in order to break the degeneracies and to make the exploration of the parameter space as clear as possible and as efficient as possible. From these effective parameters, we recomputed the parameters of the Lagrangian, which we input, okay, in our numerical code. Now, after computing the numerical power spectrum, we could input this numerical power spectrum to the Einstein-Boltzmann solver that computes the CMB power spectra, and then we could compute the likelihood, and we sampled the likelihood using a nested sampling. Now, traditional MCMC techniques don't work in this context because of what I was saying before. So we have to expect multimodal posterior distributions, and the exploration of the parameter space is not simple at all. Okay, so we had to come up with this pipeline, okay, which was a central part of our work. Once we set it up, we could actually compute. We could actually look for these features into the data, and this is the result of our feature analysis to the data. So you see that, again, as I was anticipating before, the posterior distribution of the feature parameters. One is the overall amplitude of the of the signal, the other one is the mass of the scalar field, and the other one is the time at which the scalar field is excited during inflation. Okay, you see that we don't have any detection of these parameters, and this is because, but we have some hints. Of course, the posterior is very multimodal. You see that the amplitude of the signal is consistent with zero, but we do have some hints at very specific values of n0 and this mass of the scalar field in the data. And in particular, we see that this is the best fit the scalar power spectrum. We get a very large improvement with 3 parameters. We get a very large improvement of the chi-square, nearly 14, which is quite remarkable for 3 parameters. But again, if we from a model selection point of view, this model is not favored over the lambda CDM precisely because we have 3 extra parameters. Nevertheless, you see that it can indeed address some of the features, some of the residuals in the data, okay, both in TT but also in E and TE. And this is precisely why we get such a large improvement in the fit to the data. Okay. Now this is just for the model, but there are a plethora of feature models that are motivated by the data, by theoretical works in the past. And for example, this could be a selection. Okay, so we could have, for example, a dip in the power spectrum, or a bump, or resonant features like an extra monodromy. We could have sharp turns in the field space. So in our paper, we considered all of them, and we performed the Bayesian analysis for all of them. And it turns out that the best feature model to date is indeed the model that I presented before. This is precisely why I presented that one and not the other ones. Okay, so all of these models, of course, improve the fit of the data, but some are more disfavored from the model selection point of view, and all of them are described by 3 parameters, but none of them improves the fit in the same way as this classical primordial standard log. Also, we have some other models that are better at fitting the low L anomaly that I showed before. Okay, these are, for example, like a step or a kink in the potential. Okay, and you can see that they address the residuals mainly at low L without changing significantly the higher L. Okay, so it would be desirable to say, but to understand, is there? So these are the hints that we have in the feature in the data. Okay, some of these models provide a better fit. Some provide all the models provide a better fit than lambda CDM. Some of them provide a much better fit. Some of them provide a comparable fit. Now, there could be essentially the situation could be either that these features are really there in the data, and the data simply don't have the constraining power to detect them. Okay, so we need more precise data in the future, or they could be just statistical flukes. Okay, so this is the final question that I'm going to address in the last 5 minutes of my talk. Is there a future for these features? And I argue that the answer is positive. And the reason is that, sticking to CMB data, we have some planned experiments in the future. Some of them will be ground-based, mapping smaller scales, and then there will be Lightbird, which is going to be space-based and is designed to map the larger scales. Now, all these future experiments are designed with the precise goal, with specific goal of detecting B modes. But in order to achieve a detection of the B modes, you also have to increase your sensitivity to E modes. And you can see some sensitivity curves here in the upper panel compared to the sensitivity of Planck, which is plotted in black. And these sensitivities, from these sensitivities, you can compute projected error bars, and you see that they will increase significantly over current error bars from Planck. And because of this, and because of what I said before, right, E-modes are a much better detector of features. Okay, so we essentially explored the capability of these experiments to detect primordial features. So what we did in our analysis was to assume, we did many more analyses, but what I will present in this talk is just a snapshot of that. So suppose that, again, the best fit to the data that we found, which is given by this classical primordial standard log, is indeed the true model of the universe. are future data going to detect it or not? Okay, so we performed a forecast. It was a nested sampling forecast, so beyond a feature one. This is just a technical aspect. And we assume this model as a fiducial. Okay, and you can see how much the constraints on this model will improve. In particular, you see that we will be able to detect the amplitude of the feature, its location, and we will be able to constrain very tightly the mass of the scalar field. These are posterior distribution on the model parameters, but if you want to have an understanding of how much we can constrain the power spectrum itself, you can see it from here. So you can see that Planck data, which are shown in black lines, are essentially very consistent with the near scale invariant power spectrum. But in the future, if we assume this model as a fiducial, we will be able to reconstruct the very oscillatory behavior of this model. Okay, so we will be able to detect this type of signals in the data. And in particular, what we will also learn a lot about what's going on during inflation. So in particular, in the context of this model, we will be able to detect a massive field with a mass which is 18 times, and I'm saying the number 18 and not 20 because the constraining power will be accurate enough to distinguish 18 from 20, essentially 18 times the energy scale of inflation at more than 5 sigma. Okay, so it will be a very, very, very nice information that we will gain with future experiments. Now, this is by assuming this model, but then we will be able also to compare the other feature models to this fiducial. Okay, and as you can see, the constraints on these models will be bad essentially because there will be no evidence for these models. Okay, so all the amplitudes are going to be consistent with zero. Now, if you consider a resonant feature signal, interestingly, we will have a peak that corresponds to a frequency of 18 times the Hubble scale inflation. But again, it won't be a detection; it will be just a hint. Okay, so using the wrong model to compare the data, we will get this. And this is why also it is absolutely important to model the feature in a very precise way. And we had to, of course, resort to this numerical pipeline. And this is just another model selection table that is going to show that while we have only we don't have evidence right now for feature, in the future we will be able to to, uh, to detect these models or rule them out. We are very strong to decisive statistical significance. All right, so I'm done with my thoughts. So these are essentially my conclusions. So features, I hope that I convinced you that features carry invaluable information about the dynamics of the early universe. They're not, right now, we don't have statistical significance for them in the current data, but we have very, very interesting best fit candidates, and they will be detected by future CMB experiments. Now, this is not just, however, so the story about these features is not just restricted to CMB, in particular, and to the primordial power spectrum. In particular, all these types of signal will show up also in higher order correlation functions, such as, for example, the bispectrum. Okay, and in particular, if you look at this plot from Planck, you see that we have a peak of significance precisely at the frequency of the massive scalar field that I showed before. Also, we have other data at large scales that are starting to be competitive with Planck from large scale structure, for example. This is something that I'm currently exploring. And then we have a very largely unexplored territory at smaller scales, and we can have something similar happening also already there. Of course, because the sensitivities that we are talking about are completely different. Right here, I'm showing all the experimental sensitivities that we have at large scales. We need to consider some models that are a little bit more, not necessarily fine-tuned, but that they are in a regime which is different from what I showed today. But there is a lot of interesting stuff going on here, and I think that all these experiments at smaller scales will be a very interesting leverage on the physics of primordial features. Okay, and I'll leave you with this plot. I think I'm done. Thanks a lot for the attention.
Okay, so thank you for the nice talk. We have time for question answer. Any question from the audience? Please unmute yourself and ask. Okay, I have a couple of things that I was wondering about. So one of the things, so which I was trying to understand. So you're taking a presence of some extra scalar field which could affect the primordial features, right? Is
Uh, Not always, but in the model that I showed, this classical primordial classical standard clock model, yes, we have two fields. One is the inflaton, and the other one is a massive field. Yes.
okay. So this massive field, typically, if it's very heavy than, let's say, the Hubble, then it doesn't oscillate and that doesn't contribute to this feature, right? Only when
Yes,
it's
sir.
light, then you see um, this oscillating features. Is that correct?
Not really. So I agree with the first part of your sentence, and indeed you see that the field starts out. The field is stabilized at the beginning of inflation. Now, what happens is that we have a sharp feature. So the sharp feature injects some energy into the scalar field, into this massive field, and so it starts oscillate. But because it's heavy, okay, it relaxes down at the bottom of the new effective potential. Okay, so its dynamics becomes important only for a very, very, very short time.
I see.
So the field is really massive. But yeah, I agree. I mean, if there was nothing there, it would stay at the top, at the bottom of the
Okay, so
potential, and it wouldn't contribute to
so
the
so
dynamics.
then my so then my question is that, so this field which has this features, I mean, field in the sense that it's goes to the bottom after a while, after this feature has gone. So then to expect that at some length scales this feature will be different, and some, sorry, no, not the feature, at some length scales the value of this scalar field, the value will be different, and at some other length scales the value will be different. So in that case, if you try to do a 3-point function, then I mean, you might end up having some correlation between large scales and small scales, right?
Yes, absolutely. Though this is going to produce some interesting scale-dependent non-Gaussianities.
Yeah,
Yes.
yeah, not only scale dependent non-Gaussianity, but perhaps you could also start to see this oscillating feature also in the non-Gaussianity itself, right?
Yeah, exactly. That's what I'm talking about. Yes. So this feature. So this is so right now I'm just considering the primordial power spectrum because this is what is better constrained by the data. We don't have. I mean, we have detected the primordial. We have detected the power spectrum of the CMB. We haven't detected the bispectrum.
Mhm.
But this feature is going to show up in all higher order correlation functions of these fields, and all higher order correlation functions will show this
Right,
oscillatory
right.
pattern.
Yeah,
Yes.
this is what I'm imagining. And typically people have proposed this. I mean, it may not be exactly same as putting a feature like this. So you have put this feature in front of the kinetic energy term, right? It's this capital. Um, Sorry, what is this?
Yes.
Right.
This is a heaviside theta. So essentially, this is like, I mean, we chose that to model this kind of trajectory. So at some point, we turn on a curve that, at some point, we just curve the trajectory.
Right. So
But this is not necessarily the case. We could have something which is more similar to, for example, this one. Okay.
yeah, I understand. So yeah, so the first case is like a turning point, sorry, turning rate kind of a thing where you generate the turn, and this is the rate. But yeah, so what I was mentioning to you is that people have also explored this kind of possibilities in something which is known as cosmological collider physics. If you are
Yes,
aware.
I am familiar with this. Now, the difference between the cosmological collider physics and this one is that, and in fact, there is a work by a colleague of mine, Shingan, who
Mhm,
considered the classical cosmological collider, but this is
mhm,
another story. So the point of cosmological collider physics is that you don't have any signal in the primordial power spectrum because these are quantum fluctuations of massive fields. So you don't here instead you are exciting. This is
Okay,
a classical oscillation
I
of
see,
a
I
massive
see, I
field.
see. Okay, so you put the oscillation right at the classical level, like Lagrange, right? So
Exactly, precisely,
coming from
precisely.
the field
Yes.
itself. This is not coming from the memetric. Okay, I understand. I understand.
Yeah, so cosmological collider physics, even if you have a single field slow roll, then because of the expansion of the universe, you have quantum sorry, scalar fields, massive scalar fields, which are oscillating quantum mechanically. And they produce a very specific, which is in fact the very same type of, they're always massive fields. So the signal that you see in the squeeze limit of the bispectrum is always of the type m over h log k, which is
Yes,
precisely the same that you serve
yes.
here. Now,
Because this is like the Boltzmann, right? This is like a thermal radiation. Instead of thermal radiation, it's like a quantum radiation, and this is just
exactly.
like a Boltzmann thermal distribution.
Exactly. So the two effects are related, but this is the difference is that this is a field which is oscillating already at the classical level.
Mm-hmm, mm-hmm.
So in a sense, the kind of signal that you expect is stronger than the quantum
Right, right.
mechanical one.
I understand. I understand. Okay. And in that case, the cosmological collider is what matters is whether the mass is close to the Hubble or greater than Hubble or less to Hubble. Only in the
E-
level is very close to the Hubble you see the signal of cosmological collider, or else you don't.
Exactly, exactly. You're right, and I think the point of the cosmological collider is that you have a very high, as you said, Boltzmann suppression. So it's hard to test some masses which are much larger than Hubble.
Yeah,
So
yeah.
you only test. Whereas here, you see this. We could. I mean, I showed you the best fit, which is m, which is like 20 times, nearly 20 times the energy scale of inflation. But in principle, you could have also, we have also some best fit candidates of m, which is 100 times the Hubble, and this is because it is not as suppressed as the cosmological collider
I
signal.
see. I see. Okay. Okay. Mm, I have one more question, which is related to the fact that mm, if instead of a scalar field, if you have you explored the possibility of having a vector field?
No, I've never explored that. I mean, it would be it could be interesting. I don't know why should we expect. I mean, I think that we could model features also in the case of a vector field.
Yeah, so apart from modeling the vector fields, the reason of I mean, one of the motivations of vector field is
Okay.
it might induce some kind of correlation between the scalar and the vectors, right? Because you are in any so if it's a massive vector, you will have a longitudinal part which is like a scalar, and then you will have
Hmm.
two other degrees of freedom which will behave like an actual honest, like honest vector, right?
Okay. Hmm.
So then one might end up having some correlation between um, the E and B and T that you were mentioning, because some will be sourced by the vector part and some will be sourced by the scalar part, and there could be some interesting correlation between T, E, and B, which here you don't see because here it's everything just done
Yes. Okay.
ambiguous system, right?
Okay. Yes. Yes. Yeah, I've never considered that. It could be interesting.
Okay. Any other question from the audience? Please unmute yourself and ask. Okay, if not, then one last question. So at the end, when you were showing the gravitation wave,
Hmm.
the plot where you're showing that this very small scale, so this K tend to
Yes. Let me
much
go back
smaller
to.
than make K much greater than the, yeah.
Yep. So this was just a flash because it's not something that I discussed during the talk. But yeah, let me see.
Okay. So
You were talking about this one, right?
mm, is it? Yes, and there was also the last slide, I think the last slide.
This one. Okay.
Yeah, yeah, here. So here, when you talk about detecting using gravitation waves, which is, let's say, Lisa or Einstein telescope,
Hmm.
here, are you talking about the primordial gravitation wave in the sense these are first order tensors, or these are induced by the scalars which you have in your?
Well, it really depends on the. It's going to be some. Let's put it this way. So it's not a linear order effect. It's going to be a second, as yeah, like a scalar-induced effect.
Okay.
So if you have, so for example, if you have something like this, then you produce. This is the
This
second order
is
scalar-induced gravitational wave
yeah, this
produced
is where
at.
like this is like p zeta square, right? Roughly.
Exactly. This is like zeta squared. It's produced by at horizon reentry. You could have something going on already during inflation. Okay, if you have a sufficiently sharp feature, so things could be a little bit more complicated than that. But yes, it's always some kind of scalar induced gravitational waves that I was talking about. Yes,
Okay, and here also the non-Gaussianities might play a big role because these,
a huge role.
yeah, I
I
mean,
agree.
it's just a square if non-Gaussianity is zero. If it's not, if it's more, then you have base plus, I mean, some other contributions. And here, do you expect that not only the magnitude of the non-Gaussianity, but one can also talk about looking at some of the shapes, like folded shapes or some other non-trivial shapes that in the usually in the CMB or the 21 centimeter we are not able to do because it's the, I mean, the range of frequencies or range of k values we are exploring are very limited, right? It's just
Yes.
little bit around 0.056. But with this Lisa and Einstein telescope, we will be probing probably quite large decades of k, like probably two or three or five orders of magnitude of k.
Yeah,
So probably it's not only the magnitude but also shapes that one can.
I agree. I agree. Yes.
Okay. Thank you for the nice talk. If there is no other question,
Thank you.
will you be able to send us the slides?
Yeah, absolutely. I'll do that straight away.
Okay. Okay. Thank you.